It can be satisfying, it can, but it's not always easy. In the office, there are two printers which have multiple tools, the Snapmaker U1 and the Bambu X2D. There are obvious differences between these printers, but both are designed to print multiple materials in the one print, and they're both the same price. It might seem obvious to go for the U1 given the extra tools, but the X2D was designed specifically for printing a dissimilar support material. So let's see how it fares against a tool changer. This video is both a tutorial on getting great results with a dedicated support material and seeing how both of these printers deal with various materials. And the catch is we're not printing with BVOH, PVA, or HIPs. We're printing supports with what you already have on your shelf. Standard filaments, PLA, PETG, ABS and such. Because they're more affordable, they're more available, and they have greater receptibility to recycling. For our tests, we're doing several different kinds of geometries. Standard flat overhang, the easiest kind of support task. Tiny parts. The smaller the part, the less surface area, the less adhesion. They can be tricky. Stacked parts. Ever want to print things one on top of another? You can, and it saves time. Sharp angles. Sharp angles mean quick direction changes which can loosen support interfaces. And we're also doing a more complicated organic geometry. And because we have the X2D with a chamber heater and enclosure, we're not just testing PLA, PETG and TPU, we're also trying ABS, nylon and PC. And we'll throw in PP for good measure too and a little bit of masochism. Okay, basic settings guide first, just the relevant settings for getting started. If you have never done this before, then this is for you, and we're going to start with PLA. The best support material for PLA is of course PETG, and you probably knew that. Load in your part to your slicer, and this is our standard flat overhang test. It's literally just two elongated cubes kind of squished next to each other, and there's a gap of less than a millimeter for the interface. It's just supposed to be simple. Turn on your support, and for a standard flat surface you want normal supports, because then you can choose snug style, which compacts the support structure and only keeps it where you need it. For other geometries, it may be different, but what is more important are the interface settings. Choose your filament for support. PETG should be your interface, and you can choose PLA to be your base support material if you want. It will eliminate the need for a material change, and if you need to save your interface material, that can be useful. Also, because your prime tower will have both materials in it for most of the print, if you choose to use PETG as both, it could cause problems if the two materials don't adhere to each other. For our purposes, we want to get everything right, so we're going to use PETG for both. Ironing your support interface is great. It makes the underside much smoother and it makes it easier to remove. However, a smoother surface means less grip. It adds print time, and it can only realistically be used on flat interfaces. Your top and bottom Z distances should be set to 0. We don't want any gap here so that we have the smoothest bottom layers. Support walls. You can add a wall to your support structure for extra rigidity. For PLA and PETG, it's probably not that necessary though. Base pattern is exactly what it sounds like. Now this can have advantages when choosing for rigidity or filament savings. Your interface should be a minimum 3 layers. Adding extra layers allows you to grab them easily for removal. It adds a strong continuous barrier to keep the part and the support material separate, and it can better tolerate errors on the Z or any warping that might occur. And warping can occur, which we'll discuss later. For interface pattern, the default is rectilinear, and I think it's the best. Rectilinear interlace is supposed to aid adhesion, but I haven't noticed a strong effect. Concentric has poor adhesion, and grid doesn't really give a nice bottom surface. Your interface spacings should be 0. This will make a totally solid and monolithic interface. If you're wondering why your top interface spacing is grayed out, that means you have ironing on. Turn it off. The XY distance is contentious. It adds a spacing between the support and the model. For this geometry, it doesn't matter that much, but we'll talk about it later. These are all the basic settings you need for supports with dissimilar materials, but they will vary depending on the material combination you use and the kind of geometry you're applying the supports to. Okay, let's see how that goes for our simple flat overhang with PLA and PETG supports on our Snapmaker U1, which we've called Tullius Caesar. Okay, here we are with our Snapmaker result, and the bottom part actually comes off super easily, and it's really nice and smooth. Here comes the peel. Yeah, that is nice. That is smooth. I'm satisfied. And now we're going to try it on the X2D, which we've called Emotional Support Panda.
It's my emotional support panda.
Oh, that's nice. Yeah, that is a very, very clean result. I'm pretty happy with that. Basic settings win. Well done. Another kind of geometry is tiny parts. Printing tiny parts is pretty much the same as simple overhangs, but getting your part to stick to that support material or vice versa can be more challenging when there is such little surface area. There are some tricks to help it though. 1. Slow down not just your interface speeds, but also the first layer of your part above the interface. It can pull on it and dislodge it. Support speed should always be low, but your part speed above is often overlooked. 2. Print hotter, and I'm speaking again about your part as well as your support. There are two ways to do this, either bump up everything or use a modifier. Unfortunately, they both have disadvantages, and changing temperatures with modifiers in Orcaforks is unfortunately not possible. You're probably better off with the first option. Okay, we're starting off with the Snapmaker and the tiny parts, and it's actually kind of hard to remove because they're so small. Eventually, it is possible. We got pretty decent results. There's good adhesion. You can easily remove it. First layer on the part above the interface looks pretty nice. Yeah, success. Let's see how Bambu does. Absolutely perfect. Okay, next up is stacking. Stacking is super fun. It's really useful for printing lots of flat objects one on top of the other. Who says you're limited to printing one flat 256 by 256 object on your build plate? Print 10. Everything settings-wise is pretty much the same here, at least for something like a cube. The only difference with this cube is that it has chamfers, so the support is getting really close to the sides of the model, unlike the previous examples. This is where the XY distance is going to be crucial. Let's see how easy it is to break off. Okay, top part comes off nice and cleanly, and that's a pretty decent surface, I think. Sides, however, are more troublesome, and I actually have to use the flush cutters for this. The problem here is that the PETG is right up against those chamfers, and it's impossible to get out of that Z hole in the middle. Don't forget that PETG tends to expand as it's extruded, so this can cause problems, and it is why your XY distance is very important. Let's see how Bambu does. This one was quite a bit harder, actually, to take off, but eventually I did get it. And the surface was very smooth, actually, like really good. There was only a tiny bit of deposition from the PETG in the bottom surface, but yeah, it was almost perfect. Well, once again, I did have to use the flush cutters to remove the excess, and I did manage to get it out of the Z hole, but there is still the problem of the XY distance with the PETG. Basically, the moral of the story is tune your XY distance when you're using PETG as a support. Should work just fine after that. Next up is sharp angles. A sharp angle can introduce peel forces to your interface and the bottom layer of your part. As we'll see later, the problem actually isn't the bottom interface, it's the top interface, or rather the first layer of your part that's going to happen right above the interface. That's the part which has the most dramatic direction change, and it's going to pull up your interface layers a little bit. So there are two things that are important here. One is reduce speed for your first layers, and the second is have a beefy interface. The Snapmaker pulled it off pretty well, and I actually can't see any problems besides a tiny bit of warping. I'm also happy to say that the X2D performed admirably. Nice. Last test with PLA is more organic. Now I realize that using dissimilar breakaway supports are typically meant for less organic objects, but I couldn't resist it. This will test flat overhangs, curved overhangs, sharp corners, creviced and embedded parts, and small parts all in one print. May God have mercy on my soul. I was actually a little bit surprised that this came off so easily. I was quite nervous about this part. The bottom interfaces came off really smoothly and left a weird turtle-shaped support structure. The surfaces on top were great, almost perfect actually. Flat parts also totally perfect. There was only a little bit of overhang issue on the head, but other than that, it was close to flawless. The X2D results were also pretty much the same. Really good actually, and actually slightly easier to remove than the Snapmaker parts. One interesting thing that you notice from this is that it's very shiny on top, where the PETG kind of insulated the PLA, making it more glossy. It's the kind of thing that happens when you increase the temperature to above normal on the PLA, but that wasn't the case with this print. So that's PLA done, and PLA is pretty easy when you're using PETG supports. So you might think that using PETG with PLA supports is just as easy. Well, not exactly. Let's check it out. So the first part of the print actually just fell off pretty much as soon as I took it out. Surfaces were totally perfect, and then we did the peel, and it's flawless. Like, I can't really see anything wrong with that. It's just perfect. And I can say the exact same for the Bambu attempt. Just perfection. So what was I talking about with that difficulty? Well, let's move on to tiny parts. Oh, God. Okay, yeah, this is why I did the tiny parts test. So the problem, again, is not really with the bottom interfaces or with the top interfaces. It's with where the PETG begins above the top interface. And because PETG likes to expand as soon as it's extruded, it doesn't really have anything to grab onto on the sides. Not that much with such a small area. So yeah, it just loses adhesion and falls off. With slower settings and possibly less moist filament, it actually worked perfectly. On the X2D side of things, we also had pretty decent results. No problems with removal, adhesion was great. Yeah, perfect. Next up is the stacking test, and we had some poor adhesion with the PLA on the PETG there, but didn't seem to make a big difference. Everything came off pretty well. Adhesion was enough, and it was removed very easily. When we were removing the top PETG part, however, we can see that there is not a great surface on the chamfers, and also there is a significant amount of deposition on the chamfers as well. Now, the bottom surface is totally fine, but the problem here is, again, the XY distance. We need to fix that. So for the X2D test, I decided to increase the XY distance considerably. So it defaults at 0.3, it's now 0.45, and it came out actually beautifully. There was no problem removing the interface, and there was no problems with adhesion. And look at that surface, it's perfect. Awesome. We also had pretty bad results with the sharp corners test. It was easy to remove, but there was a little bit of warping. And when removing the actual interface, you can see that the bottom surfaces are a little bit gross. Again, this is due to the adhesion between the bottom layers of the part and the top interface layers. But the PETG is also pulling up the parts at the sharp corners, resulting in that warping. We did it again with slower speeds, and it actually came out almost perfect. Nice. The X2D also came out pretty okay. Like, it was okay, mediocre. I wouldn't say it's perfect. There's a bit of bulging on some of the bottom layers. Otherwise, it's fine. Next, we have our turtle stack, and this came out okay, actually. The surface quality on the PETG was all right. I actually forgot to put on pressure advance for this test, so it's a bit gross at the back. Don't look at it. Yeah, it was a bit difficult to remove, but we did get it out, and there was no major problem with that. Bottom surfaces aren't that clean, though. It bonded a bit too much. The X2D results were quite similar. It was a little easier to remove the parts from the support, but we got some deposition on the PETG. The bottom parts, however, were actually much better than the Snapmaker parts. A little bit of deposition, but otherwise it was really good. So here we are with the Snapmaker and printing TPU with PLA support. And it comes off nice and smoothly. However, I do notice there is a little bit of deposition of the PLA on the bottom surface. Otherwise, the surface came out very cleanly. Yeah, it's good. Moving on to the X2D with TPU and PLA, and it is pretty much the same. We have no deposition this time, which is great. That looks nice. Okay, now we're on to the Snapmaker with the tiny parts. And again, it fell apart pretty much as soon as I took it off the build plate. You can remove these pretty easily. There was no issues with adhesion. Everything came out really well. Yeah, top marks. The Bambu parts came out pretty much the same, although a little bit harder to remove. And here we have the stacking test with the Snapmaker and TPU and PLA. And it comes off really smoothly. There's a good top layer there. No embedding in the Z. The interface comes off really smoothly, and that is a smooth, sheeny bottom surface. That looks nice. The X2D results were great. There was no issues with the chamfers, and the bottom surface was perfect. Okay, now we're trying the sharp angles, and that came out okay. It's definitely not perfect. We got some bad adhesion. I think it warped slightly, and yeah, it's not so smooth. And on the Bambu, yeah, it came out okay. Like, it's not as... It's better than the Snapmaker for sure, but it's not perfect. You can see that there was a little bit of a warping, and that caused some detachment. TPU actually behaves similarly to PETG. So when it does get extruded, it expands a bit, and all elastic filament has this. It's just a question of severity, and the sharp angles just exacerbate this. So again, speed is key here. We're doing the turtle now on the Snapmaker U1, and if you look closely, you can see that the TPU is starting to get a little bit moist, and this can be quite an issue for adhesion. Results came out pretty well though. There was no real issues with the moisture affecting adhesion. The moisture problem continues with the X2D, but again, no major problems with adhesion. It was quite easy to remove the support structure from the bottom part. However, it was a little difficult to remove the turtle from the top interface structure. I think moisture can affect adhesion in different ways depending on the filament, because I've noticed this filament getting, actually the adhesion becoming better with the moisture. I'm not sure why, but I have noticed with other filament as well that the adhesion gets worse. Luckily, no major problems with this, and I'm pretty happy with how it turned out. We're now moving solely to the X2D because we're printing high-temp materials, and first up is ABS. And ABS is difficult because of the high temperature, both in terms of the filament temperature and the chamber temperature. The X2D has a chamber heater. I am using it to get the best results with the ABS. So with this challenge, I can't use PLA. It will just warp or get stuck in the hot end. ASA will just bond to it. TPU, maybe, but I don't like the idea of using a flex filament for support. I'm only really left with PETG as an affordable option. So here we go. And that worked almost perfectly. I was very surprised. Like, that's almost perfect. There's a slight amount of detachment in the center, I think. Yeah, nice. However, moving to the sharp corner test, yeah, that didn't work so well. It literally bonded to it. I couldn't get it off at all. Yeah, I had to resort to unconventional techniques. And yeah, I gave up with it. And I tried it with the tiny parts as well, and the exact same thing happened. So I was very depressed. Sad panda. But I have a trick up my sleeve, and it's called PLA. Now, if you've just gasped in horror, don't worry, let me explain. I have tried regular PLA, and of course, a 60-degree heated chamber does not play well with it. And unclogging the X2D is not a very enjoyable process, so don't use regular PLA. This is actually a HD PLA. Specifically, it is Polymaker's HD PLA which is heat stable up to 150 degrees. To be honest, it is still PLA and there may be risks, but so far we have had excellent results. I'm going to keep testing with it, but I'm very impressed with how well it works. Next up on the chopping block is nylon, and we're using PA12CF here. PETG is a bit too heat intolerant for nylon, so we're bumping up to ABS as our support, which actually worked perfectly. Like, awesome. The tiny parts also came out really well. There was no problems with adhesion. A small surface area apparently is fine with ABS and nylon. With sharp corners, it wasn't totally perfect, but it was okay. There was, again, a little bit of warping on the corners. And turtle test came out really well, actually. It was a tiny bit hard to get out, and there was some crevice parts that needed some encouragement. But otherwise, that worked out really well. Bottom surfaces came out lovely, and everything else came out lovely. Nice. PC is next, and someone once told me PETG works well. I can confirm it does not. I also tried ABS, and it welds, so affordability is out for PC, and I had to choose nylon. And actually, that worked perfectly on our standard overhang, like, beautifully. And yes, I know nylon is not cheap, but I'm out of options here. The problem, however, is that in further testing, it did not work. You see, nylon warps, and when your prime tower experiences warping on every second layer, things go bad fast. So I moved to a more rigid nylon. This is PA12CF, and it works with a caveat: carbon deposition. Bits of carbon and polymer can very easily get stuck in your part. So not the best results, and I'm not even doing the turtle test for obvious reasons. Last thing we have is the demon of adhesion, the slickness of stickiness, the bane of, you know what I mean, it's polypropylene. Nothing sticks to polypropylene. Nothing. Doesn't even stick to PEI. It won't stick to any affordable filament I have. This is completely futile. I don't... Oh, okay, turns out TPU works. It's far from perfect. It does warp on the corners, and that can possibly cause a fail if you have more complicated parts. And with tiny parts, it's worse. It needs the surface area. With sharp corners as well, it's not going to work that well. As mentioned before, I don't like the idea of using a flex filament as support, but we have options. If we want to make a support more rigid, we can. In Orca Forks, we have support walls. Just add more walls to your support. There is also expansion, make them bigger. You can also not choose snug supports. It doesn't make it perfect, but it does offer you a support material for polypropylene that is affordable, and you probably have a spool at home already. But, well, hips might be more reliable. And if you're wondering how the X2D went, well, it didn't. Because of that Bowden extruder, I can't get reliable extrusion out of the polypropylene. So that's off the table. Still, I am very glad I tried this, because maybe I can't make 2PU work as a support for polypropylene, but I might be able to make it work as a raft for polypropylene so that you don't have to use a polypropylene sheet or polypropylene tape on your PEI. Instead, just print a TPU raft and then print the polypropylene. I'm going to work on this. For PLA, PETG, and TPU, the basic settings are okay. PETG should have its XY distance tuned for sure and slow down accelerations and reduce temperatures where there are sharp angles. And the same can be said for TPU, but to a lesser degree. The higher temp materials are a lot more interesting. So for ABS, it was difficult to find a good support material, and I'm still a bit hesitant about using PLA. But so far we've had great results, and there was no need to change any settings beyond the basic settings. The only thing I might change would be to increase the temperature of the ABS a little bit to aid adhesion. But slicers don't like it when you mix a low temp filament with a high temp filament, so you will need to access the preferences and remove the restriction on mixing them. Nylon was simple. ABS works so well as a support material, and there was no need to change any settings at all. It worked perfectly. Polycarbonate was a shit show. I'm not fond of using nylon as a support material, and nylon carbon fiber is even worse. Yeah, unfortunately, I failed pretty spectacularly when it came to polycarbonate, and I cannot really recommend a affordable or available filament for it as a support material. You're probably better off just using HIPs. Polypropylene was challenging, as one might expect, and TPU has limited reliability. It is still cool to know that TPU can work as a support material for relatively simple geometries with polypropylene. Polypropylene does not like overhangs at all. So should you start using these as a support material? Not necessarily. In a lot of cases, it might actually be better to use the same material for both model and support. If you're going to be doing some post-processing on your part, it might not even be necessary to do this because you're going to go over any marks that are made by using a support material that's the same as your model. I think there is a lot more that can be done in slicers for multi-material support. A concentric pattern for the support body would also be useful so that you can avoid that back and forth motion on the sides. And having more control over your fan speed and accelerations for just the perimeters on your bottom surfaces, or choosing elevated temperatures just for the bottom layer would be great. As for the printers, there's actually not a huge difference in how capable they are when it comes to multi-material support. The only big difference is the U1, which as stock doesn't come with a lid or a chamber heater. So that significantly limits its potential, because if you're just printing PLA organic complicated parts that just need to look nice, then this technique is not a huge advantage and you're probably better off just using tree supports. Using this technique with nylon or ABS, however, is very helpful. That said, the X2D just can't do multi-material like the U1. It only has two hot ends and one of those has a Bowden extruder. With the U1, I like to print PETG and TPU together so there is some compliance to a rigid part, and I can use PLA as a support material for both. That's really cool. The X2D is not a multi-material printer. However, if you need to print ABS or nylon with a cheap and easy to remove support material, you just have to consider this. I hope this video was helpful, guys. Let us know what you think in the comments down below. And if you didn't know, we have a Discord server where there is printer talk on a daily basis. We'll be back with another video next week. So until then, later.